In this lecture, we're going to start talking about quadratic functions. If we want to begin that discussion, then we need to define what a quadratic function is. A function f is a quadratic function if f of x equals ax squared plus bx plus c, where a, b, and c are real numbers with a not equal to 0. You don't want a to be 0 because that would get rid of this squared term, and that's kind of one of the defining characteristics of a quadratic function. A quadratic function is a polynomial function of degree 2, where the highest power of the variable is 2. As you probably know, the graph of a quadratic function is a parabola, and in particular, it's a parabola with a vertical line of symmetry. So a quadratic function can only open in one of two ways. It can either open upward with its vertex at the bottom, or it can open downward with its vertex at the top. Now, by plotting a bunch of points, you can graph the function from the ax squared plus bx plus c form. But we want to put this in the context of things that we've already talked about before, so we're going to look at what we call the standard equation of a parabola. The standard equation of a parabola with a vertical line of symmetry is y equals a times the square of x minus h plus k. And when we rewrite the equation like this, we can put it in terms of all the transformations that we've talked about previously. The minus h is going to shift the graph horizontally. If h is positive, then you're going to shift to the right, and if h is negative, then you're going to shift to the left. The a has two possible transformations in it. Of course, that could be a vertical stretch or compression. But also, if a is negative, that will determine which way the parabola opens. If a is positive, then the parabola opens upward, so the vertex is at the bottom of the graph. If a is negative, remember that's a vertical reflection. That will give us a reflection over the x-axis, and so the parabola will open downward so that the vertex is at the top of the graph. Then the plus k will shift the graph up if k is positive and down if k is negative. So if we can rewrite a quadratic function in this form, then it's easy to graph the function. Furthermore, we can pick off important information about the function, like in particular where the vertex is. We're going to learn a second technique for finding the vertex, but it's dependent on this. We're going to prove why it works using this. So we're going to practice this technique a couple of times. First, let's see if we can just pick off the information. So in this example, we've already written the function the same way that you would write the standard equation of a parabola. It says, consider the function f of x equals negative 6 times the square of x minus 3 plus 2. Part A says, what is the vertex of the graph of y equals f of x? We have a rule written out. The point h comma k is the vertex of the parabola, where h is the number that you're subtracting from x and k is the number on the outside, the constant that's being added. So just applying that rule, we're subtracting 3 from the x, so the x coordinate of the vertex is 3, and we're adding 2 on the outside, so the y coordinate of the vertex is 2. However, I hope you can see that that's the vertex without thinking of that as a rule and instead applying our transformations from the previous lessons. The graph of this is going to be a parabola. You can tell because of the square. We're going to start with the library function x squared. The minus 3 is going to shift the graph 3 units to the right, and the plus 2 is going to shift the graph 2 units up. Now that plus 2 has to be applied after we do this part, but it's still going to shift 3 units to the right and 2 units up, and so we wind up with a point at 3, 2. That's the vertex. Part B says, what is the range of this function? You don't need to draw the graph to figure this out, but let me just sketch a quick graph of what's going on here. We've already determined that the vertex would be at 3, 2. That's over here in the first quadrant. And then the negative factor on the outside is going to give us a vertical reflection. So this thing opens downward. Looking at that graph, I know that the range goes from negative infinity to positive 2, including 2. There really is a point whose y-coordinate is 2. So you can get an output of 2. Part C says, what is the maximum output of f of x? Well, we already know that. The range extends from negative infinity to 2. So the maximum possible output is 2. It's not a coincidence that's the y-coordinate of the vertex. When a parabola opens downward, the function will have a maximum output, and it's the y-coordinate of the vertex. When a function opens upward, it has a minimum possible output, which is also the y-coordinate of the vertex. It's all dependent on the orientation of the parabola. Let's look at an example where we're not already in the standard form. This example says, express y equals x squared plus 4x plus 9 in standard form and sketch the graph. We could graph this parabola point by plugging in a bunch of numbers, but it might take a while. You wind up plotting a bunch of points until you stumble across where the vertex is. You can't do this one by finding x-intercepts because this function doesn't have any x-intercepts. So trying to graph this by plotting a bunch of points probably isn't the best option. Instead, let's follow the instructions and rewrite this in standard form. Notice that the standard form is written with a square of a binomial, so you probably know what that means. We're going to complete the square on those first two terms. Let me rewrite this and leave myself some space between the first two terms and the last term. And I'm going to complete the square in that space. How do we complete the square? We take half of the coefficient of x and square it. Some of you might be able to guess what that's going to come out to without actually doing this process. You might just know off the top of your head that x squared plus 4x plus something gives you a perfect square. But if you're not sure, follow the process. We wind up adding 4, and that completes the square. You probably know how that factors. That's x plus 2 quantity squared. But I can't just write plus 9 next to that because we've changed the function. The altered equation that I have here and the equation I started with aren't the same thing. If I were to collect these terms together, that would give me plus 13. That's not the same as what we have in the original equation. So I have to do something to counterbalance this step of adding 4. And normally we would add 4 to the other side, but that's not what the standard equation looks like. We have to have just a y over here. So we're going to do a step that looks silly at first until you recognize what we're going to do. We're immediately going to subtract 4 from the same side. Now if I were to immediately cancel these 4's, that would be pointless, because I'd be right back to where I started. But if I factor this to x plus 2 squared like we already have, and then collect these two terms together, now I have something equivalent to the original equation, but it's written in the standard form. I know exactly how to sketch this graph. I can just apply my transformations. We're starting with the graph of y equals x squared. That's that parabola that opens upward, emanating from the origin. The plus 2 will shift that graph 2 units to the left. The plus 5 will shift the graph 5 units up. So I've got a vertex at negative 2, 5. And I just draw a parabola that opens upward, and there's the graph of my function. This is the graph of y equals x squared plus 4x plus 9, and I got that by writing it in the standard form. So the strategy is to complete the square, counterbalance that step, rewrite it in the standard form, and then you can sketch the graph or find the vertex or do whatever it is you need to do. Let's look at another example where we've got one extra thing to worry about. This example says express y equals negative 3x squared plus 24x minus 11 in standard form and sketch the graph. Here we've got an extra issue because of this negative 3. We've got to get that out of the way. When we write this in standard form, the expression that's being squared is of the form x minus h. So that means we have to deal with just an x squared. Now if this expression were set equal to a number on the left side, well, we could just divide everything by negative 3. We did something similar to that when we were trying to find the center and radius of a circle. But that's not an option here, because if I divide everything by negative 3, I get y over negative 3, and then what are we going to do? We get kind of stuck. So instead what I'm going to do is factor a negative 3 out of those first two terms. So negative 3 times x squared gives me negative 3x squared. Negative 3 times negative 8x would give me positive 24x. I'm going to leave myself a little bit of space to complete the square inside the parentheses and then subtract 11. You can already see this taking shape. The negative 3 is the a in the standard equation. We're going to complete the square here so that we can get a perfect square trinomial that we can factor in this format. And then on the outside there will be some constant. The constant isn't going to be negative 11 though, because we're going to have to do that counterbalancing step. See if you can figure out what number you have to add in order to complete the square. The procedure says take half of the coefficient on the linear term and square it. And that gives us 16. Now we need to counterbalance that, and your first thought is going to be to subtract 16. I'm going to write this, but don't write this in your notes because I want you to see that this is wrong. Watch what happens if I check this. I'm going to distribute this back through. Gives me minus 48. And then minus 27, and if I collect these together, that's not going to give me minus 11. Subtracting 16 does not counterbalance this. Why? Because we didn't really add 16. That 16 is getting multiplied by negative 3. You can see it when I check my work. What that really did was subtract 48. So to counterbalance that, I need to add 48. Let me check this. This would be negative 3x squared plus 24x minus 48 minus 11 plus 48. The minus 48 and the plus 48 would cancel, and that's equivalent to what I started with. In order to counterbalance, you have to take into account that the thing inside the parentheses is being multiplied by the value of a. Now we factor. This is x minus 4 squared. I know most of you don't need a hint to factor this, but if you did, notice that it was negative 4 that we squared down here. That's not a coincidence. That always lines up this way. Negative 11 plus 48 is positive 37, so this is plus 37. And now we have this written in the standard form. This is going to shift 4 units to the right, 37 units up. It's going to open downward because of the negative coefficient in front, and it's going to be skinnier than usual because of the vertical stretch. So the basic graph will be something like this. Because it's not clear, I might label this as the 0.4, 37. So rewriting the equation in standard form gives us one way to identify where the vertex is. But there's an alternative. There's a shortcut formula for finding the x-coordinate of the vertex. The vertex of the parabola y equals ax squared plus bx plus c automatically has x-coordinate opposite of b over 2a. b is the coefficient on x, a is the coefficient on x squared. So you take the negation of the quotient of b and 2 times a. That's the x-coordinate of the vertex of the parabola. Now you'll notice that this theorem doesn't give us the y-coordinate, but to get the y-coordinate of any point on any graph, you just take the x-coordinate and plug it back into the function. So finding the y-coordinate isn't difficult once you have the x-coordinate. Now what I want to show you is that this isn't something that some nerd decided should be true. A lot of people have that misconception about math, is that somebody just decided this is the rule for finding this. A theorem like this is something that you discover. Some dork put together the logic that proves that this is true. There wasn't a big nerd meeting where they were like, we're going to decide that the x-coordinate of the vertex is opposite of b over 2a. You can actually prove this is true using logic, and it's going to depend on the process that we just used. So I'm going to show you where that comes from. Suppose you have a quadratic function f of x equals ax squared plus bx plus c. Just in general, a is not equal to 0. I'm going to follow the same process that I followed in this example and rewrite the right side so that it's in the standard form for a parabola. So the first thing I have to do is factor out the a. A times x squared would give me x squared. A times b over a would give me b. So a times b over ax would give me bx. I'm going to leave some space to complete the square, and then I add c on the outside. I have to complete the square here. How do I do that? I take half of the coefficient of x and I square it. So I'm going to write this as half of b over a. Rather than dividing by 2, I'm going to multiply by 1/2 because my coefficient looks like a fraction. So this becomes b over 2a squared, and that's b squared over 4a squared. So I'm going to add b squared over 4a squared, and now I have to counterbalance that, but remember that's being multiplied by a, so I'm really subtracting b squared over 4a. If you're not sure that that's right, distribute through here and check it, but you'll see it simplifies back to ax squared plus bx plus c. I promise you it's right. This isn't the part that I want to focus on. Now I'm going to factor this. And you might say, well, how in the world would you factor that? Well, remember the trick that I keep bringing up. You always wind up tacking on the thing that you squared in order to complete the square. So this is plus b over 2a. Again, if you don't believe me, multiply this out and check it. It'll multiply out to this. And then on the outside, we could get a common denominator and get this all as one term, but again, that's not the point. We've now written this in the standard form, and look here at the horizontal translation. We're adding b over 2a. The x-coordinate of the vertex is the opposite of b over 2a. And that's how you prove that it's true. As an aside, this winds up being the y-coordinate of the vertex, and if you want to memorize that as a separate formula, you can. But again, it's usually just easier to take the x-coordinate of the vertex and plug it in rather than to remember that formula. Here's the same equation that we graphed on a previous slide, y equals negative 3x squared plus 24x minus 11. Here, rather than putting it in standard form and graphing it, we're just asked to find the vertex. To find the x-coordinate of the vertex, we take the opposite of b over 2a. That's our theorem. That's what we proved by doing all of this math. So I do the opposite of the coefficient on x divided by 2 times the coefficient on x squared. That's the opposite of 24 divided by negative 6. That's the opposite of negative 4, which is 4. Feel free to skip some of those steps if you want to. The x-coordinate of the vertex should be 4. What did we get when we completed the square? The x-coordinate of the vertex was 4. We claim that the y-coordinate of the vertex is 37. How do you find that? Well, to get the y-coordinate of any point on any graph, you just plug the x-coordinate into the function. So I'm going to plug 4 in for x in the function. And we just simplify. So 4 squared is 16. 16 times negative 3 is negative 48. 24 times 4 is 96 minus 11. That's 48 minus 11, and there's that 37. So the vertex is the point 4, 37. Unless the instructions specifically say write it in standard form like it did in these two examples, when you need to find the vertex, I would encourage you to just use this format. Find the x-coordinate of the vertex by applying our theorem, opposite of b over 2a, and then find the y-coordinate of the vertex by plugging the x-coordinate into the equation. Here's a different way to word that kind of question. This says, what value of x yields the maximum possible output of f of x equals the opposite of x squared plus 10x plus 37? Well, first off, how do we know that this has a maximum? How do we know that the range is restricted so that this has a maximum value? Well, we know it's a parabola because it's a quadratic function, and we know it opens downward because the leading coefficient is negative. The value of a is negative. So the parabola is going to sit like this somewhere in the xy plane, and therefore it has a vertex at the top. And if the vertex is at the top, then it has a maximum y value. The y values are the outputs. This function has a maximum output. The question doesn't ask for the maximum output, though. It asks for the value of x that yields the maximum output. Well, the value of x that yields the maximum output would be the x-coordinate of the vertex. If only we had a theorem for finding the... Oh yeah, we already learned that. The vertex of a parabola has x-coordinate opposite of b over 2a. So I can just follow that theorem. The x value that maximizes this is the opposite of the coefficient on x divided by 2 times the coefficient on x squared. Don't miss that that's a negative 1 there. So this is the negation of 10 divided by negative 2, which comes out to 5. And so 5 is the input that you have to use in order to maximize this function. It doesn't actually ask us for the maximum output. It just asks us what value you would have to plug in. I do this example because we're going to do word problems soon, and some of those word problems will ask for the value of the variable that will yield a maximum result. So make sure you're paying attention to what the question is asking for. In the next example, it actually asks for the minimum output. What is the minimum output of the function f of x equals 2x squared plus 5x plus 7? How do we know this function has a minimum output? Well, it's definitely parabola, and because the leading coefficient is positive, because a is positive, this function will open upward. So there's going to be some lowest point. The vertex is at the bottom, and the y-coordinate of the vertex is going to be the minimum possible output. Now, our theorem doesn't give us a rule for jumping straight to the minimum. You can come up with such a rule. If you want to try it, you can use it. This will be the minimum. But instead, we're going to do it the standard way and just find the x-coordinate of the vertex and use it to find the y-coordinate. See if you can find the x-coordinate of the vertex. The x-coordinate of the vertex is going to be the opposite of b over 2a. A is also 2. So this is negative 5/4. That doesn't answer the question, though. That's not the minimum output. That's the input that yields the minimum output. How do I get the minimum output? Well, I evaluate the function at negative 5/4 to get the minimum. This is how you get the y-coordinate of any point on any graph. So I get 2 times negative 5/4 squared plus 5 times negative 5/4 plus 7. And this arithmetic is going to be a little bit ugly. You could use a calculator if you wanted to. This is 2 times 25 over 16. That's 25 over 8. And this is minus 25 over 4 plus 7. And I'll get a common denominator of 8. So this is 25 over 8 minus 50 over 8 plus 56 over 8. 56 divided by 8 is 7. And if I collect this together, and let's be smart about it, if I collect this together, that's 6 over 8 plus 25 over 8 is 31 over 8. So the minimum possible output of this function is 31 over 8, or 3.875. I think that comes out to 3.875. So you could plug numbers in all day. You'll never get an output smaller than 3.875. There are some other things we can tell from this by putting things together. We said this function opens upward. This is a parabola that opens upward, and its minimum possible output is a positive number. So this function must have no x-intercepts. Going back to the problem, how did I know that I had to plug the number in? I didn't do that in the last problem. Why did I have to do that here? Because this asked for the minimum output of the function. Make sure you actually answer the question. The x-coordinate tells you what you have to plug in to get the minimum output, but the x-coordinate itself is not an output. You have to actually plug that number in and get the corresponding output to determine that minimum. Okay, so this video lays the groundwork for the next lecture where we'll be doing word problems. In order to be comfortable doing that, you have to know this stuff pretty well. So if you have any questions about this, let me know. See me in an office hour or shoot me an email.